Hi guys, welcome back to the channel. In this lecture, we are going to discuss the effect of axial force on the plastic moment capacity of a section. Okay, and that section can be of beam or you can say of or column. Okay, so basically this axial force, this plastic moment can be affected by axial force, shear force, if there is material fatigue due to repeating loading, and due to some lateral buckling. So these factors can influence the plastic moment capacity of the section, and these factors are basically the secondary factors that can influence the prime plastic moment capacity. Okay, so now let us, and in this lecture we will be focusing on axial force, the effect of axial force on the plastic moment capacity. Okay, so here I am taking, let us suppose, one frame structure. Okay, and there is one W load is applied, and W load is applied at this point. So this is our column A, B, BC is beam, and CD is one more column. Okay, now due to this loading system, there will be some axial force in this column and this beam. Okay, axial force will be there in AB column and BC beam. Okay, now here I am discussing about, here in this lecture we will be taking this column AB and we will be check the effect of axial force on this column, the moment capacity of the effect of axial force on the moment capacity of this moment capacity of the cross section of this column AB. Okay, so first step, so first thing I'm assuming is that the cross section of the column is rectangular one. Okay, this is the cross section of the column. Okay, so this, and I'm also assuming that this axial load is not causing any buckling. Okay, no buckling, right? And this is the cross section of the column. This is the length of the column, and this is the cross section of the column. So cross section of the column, and let us suppose one dimension is B, another dimension is D. Okay, so now if you are applying, if there is, let us suppose some axial load is coming on this column. Okay, some axial load is there due to this loading system, and that load will be acting at the center of this column, right? So the stress distribution so initially the stress distribution on this column will look like this. Okay, if you are applying a point vertical, if you are applying a load over here, if you are applying a load at this point, right, so the stress distribution generated on this cross section will be a uniform stress distribution. Okay, will be a uniform stress distribution due to this point load P. This is the stress distribution due to point load P. Okay, and let us suppose the value of the stress is sigma naught. sigma naught will be here, sigma naught will be here. This P load is generating uniform stress sigma naught on this whole cross section. Okay. Now if you, and let us suppose this is our centroidal axis, okay. And if you apply the moment along the centroidal axis, the upper portion will be in compression and the bottom portion will be in tension, right? So this is the stress distribution due to point load. And one more thing, you can say that the neutral axis will lie at infinity. Neutral axis is what? Your zero stress axis or zero strain axis. Okay. So now if you increase the load, if you give some moment in this column, if there is some moment in this column along this neutral axis, direction of the moment is along this neutral axis, right? So upper portion, there will be some compression at this point and tension will be at this point. So now the stress diagram will modified. So it will look like this. Here you will be having sigma 1, here you will be having sigma 1 dash. Okay. Bottom fiber, due to moment at the bottom fiber there is tension, but initially you have applied this compressive force. So at this point this stress will reduce. Okay. This sigma 1, this stress sigma 1 dash will be less than sigma 1, because here there is compressive stress and tensile stress. Here both the stresses are compressive due to moment and due to axial load. So that's why this is greater than this sigma 1 dash, right? So again, this is in whole compression. This section is in compression. This whole section is in compression, right? Now again, if you increase the moment value, I'm assuming that P load, the axial force, is constant over here. This P load is constant. Okay. So again, if you are increasing the moment, so what will happen is that the stress at this point will increase and at this point it will be 0. So this is our neutral axis for this stress diagram. So this is, let us suppose, sigma 2 dash, this will be 0. And again, if you increase, because this bottom fiber is reaching toward tension, so that's why this stress distribution is showing that at this point this value of the stress is 0. Okay, so that's why this is a neutral axis, zero stress axis or zero strain axis. Here the neutral axis is lying out of the cross section, is not lying in the cross section, is not lying in the cross section, right? So again, you increase the load, you increase the moment, load you are keeping constant. So again, at this point there will be some tension generated. So let us suppose this stress is sigma 3 dash, sigma 3. So this will be sigma 3 dash. Now remember this thing, this is tensile. So direction will look like this. Here the direction of the stress will look like this. Now you can see that there is a shifting of neutral axis towards the center. Here the neutral axis lies at infinity. Here not at infinity but outside the cross section. Okay, and here it is lying just at the end of the cross section, means at this point. Okay. So again, if you increase the load, there are chances that the upper fiber at this point will start to yield. Okay, and our stress diagram will look like this. So let us suppose this is sigma y, this can be sigma 4 dash. So here this is compression and this is tension. So now again, if you increase the moment, the stress diagram will look like this. Let us suppose some fibers at bottom are also yielded. So this is sigma y. So this is again sigma y. So again, if you increase the load, the final stress diagram will look like this. Okay, so this is compression and this is tension, and this is our neutral axis. Okay, so when there is an axial force, so you cannot, this neutral axis is not the equal area axis. So this neutral axis is not the equal area axis. Why? Because there is some load, there is some axial load is there. Okay, there is some axial load is there. Although this cross section is symmetrical, but there is some axial force in this cross section. So that so this axis cannot be equal area axis. So there should be, and this and the sum this axis cannot be neutral area axis, and the summation of this compression tension should be equal to, the resultant of these two, these should be equal to this P force. Okay, that, remember that thing. Not remember, you can understand that thing, right? So this is our final stress diagram at the fully plastic state. So we will be dealing with this diagram only. Okay. So I will be rubbing all those things, all these things. So the final stress diagram was looking like this. And this is sigma y, this is sigma y. Okay. And this axis is not neutral axis, because there should be net resultant force. If this is a neutral, if this is equal area axis, then net force will be 0. But it should not be, because it should not be that case, because there is some axial forces acting on this cross section, right? So this is not equal area axis, not equal area axis. Remember that thing. Okay. So here this is compression and here this is tension, and this is our centroidal axis. And this is neutral axis. Okay. Now what I am doing over here is that we need to check the effect of axial force on the plastic moment capacity, right? So what I am doing over here is that I am dividing this stress diagram into two parts. Okay. So initially due to load, due to axial load, I am assuming that the stress diagram will look like this. Okay. So I'm assuming that due to stress diagram, this portion has yielded up to this, from centroidal axis, z by 2 from here and z by 2 from here. Okay. Because why I'm doing this, why this is symmetrical about this centroidal axis, because net force will be acting at the center, and that net force will be equals to P. This is all compression. Remember that thing. This is all compression. Tension will be start from here, below this line, below this neutral axis. Okay. So here I'm substituting what you can say that I'm dividing the stress diagram into two parts. One part is this one. Due to axial load, the stress diagram will look like this. Okay, and if you see in this cross section, this portion, on this portion, the stress diagram will look like this. The distribution of stress diagram will look like this. Okay, sigma y, sigma y, sigma y. It is uniform on this part, right? And due to moment, the stress distribution will be symmetrical. Why symmetrical? Because this is a symmetrical cross section. Okay, so this is due to moment. Okay, now if you combine these two things, these two stress diagram, you will get this stress diagram. So here also the stress at the extreme fiber is sigma y, and here also the stress at extreme fiber is sigma y. And this length, this is d minus z by 2, and this is also d minus z by 2, right? So this is compression and this is tension. Why this is symmetrical? Because due to moment, the cross section is symmetrical, and if you consider the individual effect of the moment, then there is uniaxial bending. Okay, basically the uniaxial bending is there. So due to the stress diagram will be symmetrical. Okay, about this centroidal axis, right? So this is how we break the stress diagram into two parts. Okay, this is very, very important thing. You need to understand this thing very carefully. Okay, so now this thing is done, right? Now we need to calculate what will be the what is the moment capacity, what is the moment generated due to this stress diagram. Okay, what is the moment generated due to this stress diagram, right? Or you can say that what is the contribution of the plastic moment due to this stress diagram? What is the contribution of plastic moment, which will be calculating using this stress diagram? And this stress diagram is at yield, when this cross section has fully yielded. Okay, so now, so basically what I'm doing in this part is that I will be calculating, this is the total force. Okay, here this is compression, and let us suppose this is tension. So moment will be equals to force into lever arm, right? So force will be, both the forces will be same. Already discussed, it is symmetrical. Okay, the stress distribution is symmetrical. So now what I'm doing is that, what is the total force? Total force will be sigma y stress, and this sigma y is acting on the which cross section? This B into dz by 2. Okay, on this cross section the sigma y is acting, right? This cross section. So total force will be sigma y into B into d minus z by 2. Right? There should be no doubt in this. Okay, and what is the lever arm? Lever arm is what? And these two forces are equal. That's why we are taking lever arm. Lever arm will be d minus this distance will be d minus z by 4. Okay, so d minus z by 4 plus d minus z by 4. Okay, here also this is d minus z by 4. So this is d minus z by 2. So if you, and this is d minus z by 2. So if you solve this equation, it will give you sigma y into d square by z square over में 4 into b. Okay, and if you take d common, so sigma y into d square into b over में 4, 1 minus z square over में d square. Okay, And you are familiar with this term. What is this term called? This is nothing but, this is MP for rectangular section. MP for rectangular section. So I can write M dash is equals to MP 1 minus Z square over my D square. Right? Now, this is the, you can see that this is the how the moment is varying. Okay, but we haven't included this the value of the axial force in this term. We need to, because we are calculating the effect of axial force on the moment. So that's why we need to introduce the P term in this formula. Okay, now how we will be introducing that thing we will learn now. There is a term called squash load. Squash load. And what is this load? So if you have a cross section of this column, which is B over my D, and you are applying axial load P. Let us suppose that you are applying axial load P, let us suppose. Okay. And due to this axial load on this column, this whole cross section has yielded. This whole cross section has yielded. Okay. If you are applying this load actually at the center of this cross section like this, okay, and due to this axial load, the whole cross section is yielded. Okay. So that load is basically called squash load, and the value will be PP will be equals to sigma y into B into D, right? You are applying this load at this point, this center, and it is generating a uniform stress distribution sigma y all over the structure, right? So each fiber has yielded. So that is called so this load is called squash load, in which each fiber of the cross section is yielded due to the axial force PP, not due to moment, due to axial force PP, right? And if you come to this part, due to load P, this P load value will be sigma y into Z. Okay, in our problem, what we have taken this distribution, that P load is acting at this point, the center, and it is generating this stress distribution. Okay, this stress distribution, right? So if that load is P equal to sigma y over my Z, so if you divide both the things, so P over my PP will be equals to, this is B, sigma y into B into Z over my sigma y into B into D. Sigma y will cancel out each other, B will cancel out each other. So P over my PP is equals to Z over my D, right? So in this, if you put this value in this formula, I can write M dash equals to MP 1 minus P over my PP square, right? Okay, or you can write P square plus PP square is equals to 1. Okay. So this is the final equation of between this moment capacity and this axial force. Okay. Here we have taken the compression load. You can take tensile load also. The effect will be, the relationship will be same. Okay. So this is the case. Now Now this is the final equation, m dash over में mp plus p over में pp square equals to 1. Okay. So now here you will see a very good important thing. Okay, and if you draw, now let us suppose I am taking this as a variable x and this as a variable y. Okay, this complete. So if you plot, there is a curve, the relationship, if you draw the curve between these two variables, it will look like this. Okay, and suppose this is p by pp and this is m by mp, right? Oh sorry, this is, if this is x, so this should be m by mp, and this is y, this should be p by pp, right? So now here you can see that when your load, when this p load is equals to pp, which means that your whole cross section is your whole cross section is yielded due to this axial load, then m dash value will be equals to 0, and it should be 0. Okay, because whole cross section is yielded due to axial force, then there is no use of plastic moment. Okay, and similarly, if p tends to 0, then m dash will be equals to mp, and this is we assumed while solving our problems. Okay, so this is the relation, you can show that the interaction curve between these two variables. Okay, and what is the meaning of this thing? If your application of load lies here, okay, if your loading is like acts like here, p, suppose axial force is 0, then full plastic moment will be there, full plastic moment. Okay, and if your point lies somewhere at this point, what is this point A denoting? A is denoting is what? Due to the value of this is if let us suppose this A point is denoting basically the what you can say that the combination of the moment and the axial force, which will result in the yield of this or yield of the cross section. This is showing the yield of the cross section. Okay, right? So any combination, suppose at this point this p is p1 and this m is m1, so this p1 or m1 is creating the collapse of this, is what you can say that each fiber is yielded, or you can say that this cross section has yielded due to this combination of p1 and m1. Suppose any point like b over here lies on this curve. Okay, and this load is p2 and m2, then again this p2 m2 will be resulting in yielding of the cross section. So any point on this cross section is showing the combination of the axial force and the moment that will result in the yielding of the cross section. Okay, and if the point lies inside this curve, then the cross section is safe. Then the cross section is saved from yielding. Okay, outside case is not possible. Right? So this is the what you can say that the relationship between the axial force and this moment. Okay, but in our problem we don't use this interaction, right? This interaction curve may be used in the high-rise buildings. Okay, where there is a high axial load is there. Okay, but in our normal cases we are not using this relationship. It is just I want to just let you know that how the axial force is affecting this yielding of this the plastic moment capacity of the cross section. Okay, so if you have given the axial moment capacity in case of rectangular cross section, then you can use this relation to determine the actual plastic moment capacity of that cross section. Okay guys, so if you have any doubt regarding this in this lecture, and this is a very important thing, you need to understand this thing very carefully. Okay, how this stress diagram we are getting, this is the most important thing. And again this interaction curve, what is the value if any point lies on this interaction curve, what is it showing basically. Okay, So I think I made my point clear. If you have any doubt, you can write in the comment section. Okay guys, so thank you very much. We'll meet in the next lecture.